99% of developers don't get JIT compilers. What does JIT even stand for? Jar Jar Binks in trouble? Honestly, given his track record, that's a good guess. But actually, in the computer science world, it's just-in-time compilation. Let's clear the air on something right now. The only JIT a lot of developers know is actually Git. You know, git commit, git push, git amend. There is no git JIT. They're not cousins, nor are they even remotely related. Now, you probably have a vague memory from a college course that a JIT sits somewhere between a pure interpreter and an ahead-of-time compiler. And that's correct, but it's a surface-level take. In this video, I'm going to give you the deep dive refresher that you've been looking for. I'm going to explain JIT compilers from the ground up. No hand-waving, no glossing over the details, let's get into it. When you write a program in a high-level language like Python, Java, or C++, your computer cannot run it directly. That's because your code is written for humans, using keywords like if, while, or print. But your computer's CPU can only understand machine code, which consists of binary instructions like 10111101. Therefore, your code needs to be translated into a form the CPU understands. This translation can be done in two primary ways, by using an interpreter or a compiler. Both serve the same goal, converting human-readable code into executable form, but they go about it in very different ways. Let's start with interpreters. An interpreter reads your program and executes it line by line at runtime. Instead of producing a separate file or binary ahead of time, it processes the code as the program runs. This approach allows for immediate feedback and is often used in scripting languages or educational environments. For example, when you run a Python script using the command python myscript.py, the CPython interpreter processes each line from top to bottom, translating and executing as it goes. You don't get a .exe file or any binary output. The translation happens every single time you run the script. Interpreted languages are often more flexible and easier to debug. They allow for dynamic typing and features like eval that let the program modify itself during execution. But the trade-off is performance. Since each line is translated repeatedly, interpreted code is slower compared to compiled code. The TLDR for interpreters is that you're executing code line by line. How about compilers? A compiler performs all the translation before the program is run. This is called ahead of time or AOT compilation. The compiler takes your source code and produces a standalone executable file such as a .exe on Windows or an ELF binary on Linux. When you run this file, the CPU executes machine code directly. There's no translation happening at runtime. For example, if you compile a C++ program using G++ main.cpp with the O flag followed by app, you get a file named app or app.exe on Windows. And just to break down this command, you are using the G++ compiler to compile main.cpp, and you're outputting the result as an executable named program.exe. You can run it directly without needing the original source code or a runtime interpreter. This compiled program is optimized and fast. Compiled languages like C, C++, and Rust are popular for system-level programming, embedded development, and performance-critical applications. However, they lack some of the flexibility of interpreted languages. Any change to the source code requires a full recompilation, and the binary is typically platform-specific, meaning you need to recompile for Windows, Linux, and Mac separately. The TLDR here is that for compilers or ahead-of-time compilation, you are building executables before execution. We're getting very close to JIT now. If you are interested in taking your software engineering skills to the next level, I would encourage you to build projects. I'm not talking about going down the rabbit hole of tutorial hell and building a to-do list, calculator, or weather app. I'm talking about building complex, real-world projects beyond the basics. And this is where CodeCrafters comes in. This platform provides interactive tools to build developer tooling from scratch. There are a number of courses that teach building Git from scratch, building an in-memory Redis database, an HTTP web server, your own Docker, your own DNS server, and many others. I personally love that there is built-in support for over 20 different languages. My favorite, of course, is Golang, but I would highly recommend trying a newer language like Zig as well. I'm excited to announce that I'm partnering with CodeCrafters to offer all my viewers 40% off. For more details, you can find a link in the description down below as well as the pinned comment. I'm excited to announce a special opportunity for our community this June. We're hosting a Build Your Own Shell challenge with CodeCrafters. For the entire month of June, you can take on this challenge for free. We'll have our own Coding Gopher community leaderboard to track our progress, and we'll be giving a special prize to the top finisher, plus 3 months of free access to CodeCrafters. The prizes for this contest are AirPods Pro 2, an Aura Ring 4 Black, or a Keychron Q1 Pro. Also, anyone from our community who completes any CodeCrafters challenge in June will get 5 bonus entries to win the Logitech MX Mechanical Combo giveaway. So if you're ready to build, check out the link in the description. Let's talk about intermediate representations and virtual machines. Modern languages like Java, C#, and Scala use a hybrid approach. When you compile Java code, it doesn't generate a .exe file. Instead, it produces bytecode, which is stored in .class files. This bytecode is not quite machine code. It's an intermediate form that runs on a virtual machine or VM. A virtual machine is like a fake CPU. It's a software-based CPU that runs on your real CPU. It reads and executes bytecode just like a real processor executes binary instructions. For example, Java compiles to bytecode that runs on the Java Virtual Machine or JVM. C# compiles to bytecode called Intermediate Language or IL, which runs on the .NET Common Language Runtime or CLR. The key benefit here is that bytecode is platform independent and highly portable, meaning you can run the same .class file on Windows, Linux, or Mac OS as long as you have the right virtual machine installed. This makes development and deployment simpler across multiple platforms. However, executing bytecode still requires a way to bridge the gap to actual machine code, and that's where the just-in-time or JIT compiler comes in. JIT compiler is all about compiling on the fly or dynamic compilation. A just-in-time compiler is a special component of the virtual machine that compiles bytecode into native machine code while the program is running. It doesn't translate all code immediately. Instead, it starts by interpreting the bytecode, and then as the program runs, it identifies hot code paths, which are parts of the code that are used frequently, like tight loops or heavily used functions. When such a hot path is detected, the JIT compiler kicks in and translates that bytecode into native machine code on the fly. This native machine code is stored in memory and reused. Over time, more and more of your program gets converted into machine code, making it faster and faster the longer it runs. This means a JIT compiled program might start slowly due to interpretation and compilation overhead, but it can eventually approach the performance of a fully compiled program while still retaining the flexibility of bytecode and a virtual machine. A traditional compiler like GCC has to make decisions without knowing the actual usage patterns of the program, but a JIT compiler can observe real usage patterns and tailor the optimizations accordingly. For example, if a function is always called with the same type of argument, the JIT can specialize the machine code for that case. If a particular branch in a conditional is almost always taken, the JIT can optimize for that path. These are known as adaptive optimizations. JIT systems like Hotspot in Java or RyuJIT in .NET go even further than this. They can speculate about program behavior, apply aggressive optimizations, and de-optimize if those assumptions turn out to be wrong, falling back to interpreted or safer code. This dynamic behavior makes JIT compilers ideal for long-running or performance-sensitive applications like servers, browsers, or databases. So now we've taken a look at the three primary models. Interpreters execute code one line at a time without compiling it. This makes them very flexible and good for debugging, but relatively slow. Ahead of time or AOT compilers translate the entire program into machine code ahead of time, producing an executable file like a .exe. They're fast, optimized, but less dynamic. And just-in-time or JIT compilers work within virtual machines. They interpret bytecode initially, then compile frequently used sections into machine code at runtime, combining portability and speed. So you can see that JIT compilers are very critical to the performance of modern platforms, say Java, C#, Android, and even JavaScript via engines like V8 in Chrome. They allow code to be portable and flexible while still achieving near-native execution speed. If you enjoyed this legit explanation and learned something new in this video, consider dropping a like down below and subscribing to the channel for future updates. If you're curious about finances and investing, you can check out my second channel, The Finance Gopher, in the description. And if you want to support me further in creating content just like this, I've left my Patreon as well. As always, thank you very much for watching this video and happy coding.